Hello everyone, my name is Mudit Thakre and today I am going to demystify one of the most critical processes in modern businesses, the big data analysis. The speed, volume and variety of data we collect is unprecedented and the challenge lies not in storing it but in figuring out how to turn that raw flow into real actionable value. Over the next few minutes, we will walk through the five key phases of the big data analysis lifecycle. Let's start with a crystal clear definition of what we mean when we talk about big data analytics. At its core, it's the systematic process of examining those enormous complex data sets to uncover hidden patterns, trends, and correlations. This is more than just running monthly reports. It represents a fundamental jump in scale and complexity from traditional business intelligences or BI, that is business intelligence. Where traditional BI focuses on structured data from internal sources to see what happened yesterday, big data analytics incorporates terabytes of unstructured data and from every source imaginable to tell us what will happen tomorrow. It demands a whole new set of skills and tools just to make the data readable. The ultimate goal is to move for far beyond simple reporting and generating passive statistics to create what we call actionable intelligence. We just don't want to know that sales declined last quarter. We want to diagnose why they happened and predict which regions will see the sharpest decline next quarter and recommend the exact price change needed to reverse the trend. Actionable intelligence means the output of the analysis can directly trigger a decision, a system change, or a business strategy we want to proactive, not reactive. To understand the challenge, we must understand the nature of big data itself, often summarized with the 5 V's. The first V is volume. This is the obvious one, the sheer scale of information. We are not talking about megabytes or gigabytes anymore. We are talking about terabytes, petabytes, and even zettabytes. Every second, billions of events are logged, financial trades, web clicks, sensor readings, and etc. We must architect systems that can handle the unprecedented size without crashing. Next is velocity, or the speed at which the data is generated and must be processed. Data isn't static. It's a relentless river flowing in real time from devices, social feeds, and transactions. If we wait hours to analyze sensor data from a factory flow, the opportunity to prevent equipment failure is lost. High velocity demands real time processing capabilities. The third V, and arguably the technical hurdle, is variety. This refers to the diversity of data types. Traditional systems were built of neatly organized structured data, but the big data includes vast amount of unstructured data, that is millions of customers, emails, images, videos, and raw text. Analysts must integrate and make sense of all these wildly different formats. The fourth V is veracity, which speaks to the quality of trustworthiness of the data. Big data is inherently messy. It contains errors, inconsistencies, noise, and biases. If 30% of your sensor data is faulty, your model will be 30% wrong. We must spend significant time ensuring high veracity through rigorous cleaning processes. Finally, the last V is value. All the effort, all the investment in architecture, and all the distributed computing power are irrelevant if you cannot derive meaningful value. The tangible business benefit we extract, whether it's predicting market shifts, optimizing logistics, or personalizing the customer journey, must justify the cost of managing the other 4 V's. The analysis process always begins with a clear strategy. You must start by defining the object. Ask what business problems are we trying to solve. For example, not just increase sales, but why are the first customers leaving the website after 2 pages? The hypothesis driven approach focuses your resources. Once the objective is clear, we move to the architectural design. We need a place to put all this data. This usually involves two components, the data links lake and the data warehouse. The data lake which stores all the raw cheap data and the data warehouse which stores the structured clean data that's optimized for fast reporting. As the speaker notes emphasize, strategy is 80% of the battle. A poorly questioned or a bad architecture design poisons the well later on. Phase 2 is all about ingesting the data and storing it at its scale. We use different ingestion methods based on the speed required. Batch processing handles large chunks of data periodically, like night processing of sales data, but for high velocity requirements, we use stream processing, which captures and analyzes the data continuously, such as a trading platform reacting to stock price changes in milliseconds. To handle the immense scale, we rely on distributed frameworks. Apache Hadoop provides the foundation distributed storage known as HDFS or Hadoop Database File System to manage the high velocity streaming data. Apache Kafka acts as a highly scalable message broker, essentially becoming the central nervous system for data movement across the organization. Finally, NoSQL databases like MongoDB or Cassandra are essential for storing the variety, unstructured, and streaming structured data that does not fit neatly into traditional rows and columns. We now arrive at phase 3, processing and data quality. This is often described as the most unglamorous but the most critical phase. Why? Because dirty data leads directly to flawed insights and poor business decisions. The necessary efforts cleaning the data is usually the most time consuming step in the entire analytical cycle. To prepare the data for consumption, we use what's known as the ETL pipeline, which stands for extract, transform, and load. Extract, we retrieve the raw data from all our storage systems. Transform, this is the scrubbing step. We clean it, we remove duplicates, we fix errors, and we convert every piece of data into a standardized usable format. This essential action is how we ensure the veracity of the data remains high. Load. Finally, we load that clean, usable, and standardized data into our target data warehouse, ready for the analyst to query. Beyond just cleaning, the phase also involves implementing governance protocols, rules for tracking data lineage, which is essential for auditability, and enforcing strict security measures to ensure only authorized users can access sensitive information. With our data cleaned and ready, we move to the analysis phase. We can visualize the processes as climbing an insight ladder, moving from understanding the past to actively shaping the future. The first step is descriptive analytics, which asks what happened. This is the foundation, the basic reporting, and the key performance indicator or KPIs. And standard dashboards. For example, our sales dropped by 10,000 last month, or we saw 5,000 unique website visitors in Q3. It summarizes and describes past events. Now, stepping up, we reach diagnostic analytics, which asks, why did it happen? This involves much deeper investigation and root cause analysis. We use techniques like data mining to drill down, compare cohorts, and find correlations. Continuing our example, diagnostic analysis might reveal that the sales drop was caused by a specific supply delay or a sudden dip in mobile traffic originating from a particular geographical region. The first step is the third step is the predictive analytics, which asks what will happen. This is where we introduce powerful tools like machine learning and statistical models to forecast the future. We look at historical patterns to build models that predicts customer churn, estimate inventory needs, or as we mentioned earlier, predict the likelihood of equipment failure next week. Finally, we reach the apex of the ladder, with prescriptive analytics, which asks, what should we do about it? This is the ultimate goal of big data. It moves beyond prediction to provide specific recommend and actions, often using AI and optimization algorithms. For instance, instead of just recommending predicting equipment failure, a prescriptive system might automatically schedule a maintenance order or recommend dynamically adjusting a product's price in real time to maximize profit. To execute those advanced analytics from the top of the insight ladder, we need a sophisticated tool stack that can handle massive parallel operations. The leading processing engine today is Apache Spark. It has rapidly become the industry standard because of its speed. Unlike older systems that wrote to disk, Spark performs computations in memory, making it significantly faster. Importantly, it's a unified platform, meaning it can handle everything from large-scale data ingestion and streaming to machine learning all within a single environment. Next, we rely on robust programming ecosystems. Python is a dominant language for general data science due to its versatility and rich ecosystem. Libraries like pandas are essential for data manipulation and preparation, and scikit-learn is the standard for implementing machine learning algorithms. We also rely heavily on R language. R is exceptionally strong in statistical modeling, academic research, and complex visualization. Data scientists often turn to R for deep statistical inference that goes beyond standard machine learning. Finally, we apply various algorithm types. For example, clustering is an unsupervised learning technique that groups similar data points together, ideal for customer segmentation and grouping market behavior. In contrast, classification is a supervised technique used to make discrete predictions like a simple yes or no decision. Will this blow an applicant default or is this email spam? These tools and languages are what transform the clean data into predictive models. The analysis itself is useless if the results can't be understood by the decision makers. Phase 5 is about being the bridge between complex data and strategic actions. We use high impact data visualizations, charts, graphs, and dynamic dashboards to tell the data story clearly. We rely on top business intelligence tools like Tableau, Microsoft Power BI, and which are fantastic for creating user-friendly interactive reports. The final output must be an actionable report that includes clear recommendation directly tied back to the objective we defined in slide 4. As the saying goes, if you can't visualize it, you can't sell it. Analysis is useless if it stays in a Python script. We have covered a lot about big data analysis today, moving from the definition of big data through its rigorous multi-phase lifecycle. I want to emphasize the key takeaways. Big data analysis is a continuous cyclic process. It is absolutely not a one and done project. The data streams never stops, and so our commitment to analysis and optimization must be ongoing. To recap, the entire stands on a cyclic pillar. Veracity is a paramount. We learned the success hinges on data quality. Even the most advanced machine learning model in the world will produce garbage if it's fed messy, biased, or incomplete data. Investing in robust data governance and cleaning phase 3 is non-negotiable. Scale demands distribution. We must utilize the right distributed tools like Hadoop for storage and Spark for processing to effectively manage the immense volume and velocity of our modern data. These tools are the engine that makes the whole operation possible. The goal is prescription. Our ultimate business objective is to climb that insight ladder to prescriptive analytics. That is the point where data can only tell us what will happen, but it can actively automate and optimize our decision making, proving us a powerful enduring. Thank you very much for your attentions.